Yeah, anyway, yeah, thank you for the introduction. And yeah, I'm very glad to give a talk today. And I think I should mention that I'm a mathematician. And I usually work on like a foundational problems in enumerative geometry using techniques from derived algebraic geometry. So today I'll talk about something that I'm currently working on. So this is a joint work in progress together with Adil Khan, Taski Kinjo, and Pavel Safronov. So yeah, today I'll talk about something called the Joyce conjecture. And I think it is, I first want to explain how I view the Joyce conjecture. So the Joyce conjecture is actually not about like proving some property. It's about producing or introducing a new type of structure or enumerative invariance. So I want to recall that the modern enumerative invariants like Gromov-Witten invariance or Donaldson-Thomas invariance are defined through the virtual fundamental classes. So I view this Joyce conjecture as introducing a new type of virtual classes or generalization of virtual classes that can be used to define following enumerative invariants. Firstly, we can look at the Gromov-Witten invariants. So the usual Gromov-Witten invariants are defined when the targets are smooth. So basically, Gromov-Witten invariance counts curves, or more precisely, maps from curves to a variety. And if the target is smooth, we have a Gromov-Witten invariance. But if the target becomes singular, then the moduli of stable map is not quasi-smooth in the derived algebraic geometry terminology, or classical terminology. It does not have a perfect obstruction theory. So we don't have a usual virtual classes or invariance when the target is singular. But for special class of target, we can use this new type of virtual classes, which I call Lagrangian classes, to define curve counting invariance. So we'll look at the target will be a critical locus of some function on a smooth variety. So if you have a smooth variety with function, then you can look at the critical locus, and this could be highly singular, but we can still count curve inside here. To be precise, we need some action of a torus, and the function should be of weight 1. So main example of this will be GLSM, so gauge linear sigma model. We can define curve counting invariance. Or other examples are like Hilbert scheme of points on C3, because it is hardly singular, but you can still count curves inside here. And so for GLSM, or including this Hilbert scheme of points on C3, we will get a cohomological field theory using this Gromov-Witten invariance. And now the state spaces become the vanishing cycle cohomology. And the second type of invariance will be a Donaldson-Thomas invariance. So Donaldson-Thomas invariants are originally defined for Calabi-Yau threefolds and Farnos threefolds. And it was extended to Calabi-Yau fourfold by Borisov, Joyce, and Old Thomas. What it can do with this Lagrangian classes is that we can further extend this to log Calabi-Yau four pair. So meaning that if you have a Farnon fourfold with an anti-canonical divisor, we can also define relative DT4 invariance for that pair. So in particular, we can get a degeneration formula for DT4 invariance. So this is a second type of invariance. And third invariance will be a cohomological Hall algebra. So the cohomological Hall algebra was first introduced by Kontsevich and Soibelman for quiver with potentials. And they conjecture that it can be extended to arbitrarily Calabi-Yau three categories. And last year, together with Taski Kinjo and Pavel Safronov, so we solved this. So we constructed cohomological Hall algebra for Calabi-Yau three categories. But this can be regarded as a special case of the Joyce conjecture. So this COA multiplication in this Hall algebra will be a special case of this Lagrangian classes. So this unifies the COA as well. And the last example will be, we can also count surfaces. So we can count surfaces inside Calabi-Yau fourfolds. So if you look at the Hilbert scheme of surfaces on Calabi-Yau fourfold, we can use a DT4 virtual cycle to define the surface counting invariance. But In many cases, those invariant vanishes because of the variation of Hodge structures. So DT4 invariants are deformation invariant in certain sense. And the surface class, the Hodge class, if you deform the Calabi-Yau fourfold, the surface class does not remain Hodge class in general. So it gives us a vanishing. So together with Young-Han Bae and Martin Cole, we introduced a reduced version of surface counting invariance to resolve this issue. So we remove the trivial factors coming from the variation Hodge conjecture, a variation of Hodge structures. But conceptually, our reduced surface counting invariance behave well only if the Hodge locus of the surface class is smooth. If the Hodge locus of the surface class is singular, then we expect that this reduced surface counting invariance also vanishes. So what we can do with this Lagrangian classes is that we can further refine those reduced invariants. And so if the Hodge loci are smooth, those will be the same. But if the Hodge loci become singular, then this more refined version of invariant will involve the singularity of the Hodge loci. So yeah, those are basic examples that we can define using Lagrangian classes. And other examples are like, we can also define like algebraic Fukaya categories for holomorphic symplectic varieties. So yeah, these are examples. Okay, so then now I will start. So I want to start with the motivation. So motivation of considering the Joyce conjecture. So historically, the motivation of this comes from the Kontsevich and Soberman's conjecture on constructing the cohomological Hall algebra. So let me recall the Koha of Kontsevich and Soberman. So Kontsevich and Soberman. So consider if you have a quiver with potential, from this data, they constructed an algebra, associative algebra, called the cohomological Hall algebra, which can be defined as follows. So algebra is a vector space together with a multiplication. So let me first describe the vector space. So if we have a quiver, you can look at the quiver representation variety. So you can look at the moduli space of quiver representations. And this is a smooth Artin stack. And the potential give us a function. And as a vector space, Koha is just the vanishing cycle cohomology of this function. Vanishing cycle cohomology. So to get an algebra, we need a multiplication. And the multiplication is given by the Hall product. So basically, Hall product or Hall algebra, Hall product counts the number of extensions. So we will look at the stack of extensions. So we'll look at all short exact sequences of these quiver representations. Then you can project this into middle. And if you look at other two components, you get the product of this two moduli space. And you have a function here as well. And this diagram comments. And if you see this diagram, then this arrow is always smooth. And this arrow is always proper. And the vanishing cycle cohomology has smooth pullback and proper push forward. So we can just define the Hall product by smooth pullback composed with proper push forward. Then it's not difficult to show that this is an associative algebra. So what Kontsevich and Soberman conjectured is that you can do this thing for arbitrary Calabi-Yau category. So there exists some cohomological Hall algebra for Calabi-Yau categories. So in this case, the representation of quiver with potential is in Calabi-Yau category. So it's some example, but they conjecture that this can be done in general. So here I should mention that if you look at the moduli of quiver with representation, a quiver with potential, then this is a critical locus of this function inside here. Okay. So if you want to solve this Consensus-Zolberman's conjecture, we need to do two things. We need to construct a vector space for an arbitrary category, and then we have to construct the multiplication. And the first part of the problem, the constructing vector space, was done more than 10 years ago. So let me first explain that part. Sure. Yeah, 5. So actually it's a functor, so you need to apply the constant sheaf shifted by the dimension. So then you get some sheaf, purpose sheaf. Purpose sheaf of, vanishing cycle. Yes, but this purpose sheaf of vanishing cycle is supported in the critical locus. So in that sense, you can view it as a cohomology inside here. Yeah. So let me explain the first part, the how to get the vector space. So this is called the cohomological Donaldson-Thomas theory. So let's start with an Calabi-Yau category. But the main example will be moduli of sheaves or complexes on Calabi-Yau threefold. So here, if you look at the moduli, the objects, so category will be category of perfect complexes. If you look at the moduli of objects here, and that this moduli space has something called a -1 shifted symplectic structure. So we've seen the -2 shifted symplectic structure yesterday. So this will be a -1 shifted symplectic structure. So let me briefly explain what it is. So this is the analog of a symplectic structure in derived algebraic geometry. So in derived algebraic geometry, we look at the tangent complex instead of tangent bundle. So tangent complex of this moduli space as some object E will be R home of E to itself. So we know that the tangent space are X1. So, and these higher X groups are like a deformation obstruction theory in the classical sense. So in derived algebraic geometry, tangent complex just captures the deformation obstruction theory. So it's R home. And in the for Calabi-Yau threefold, we have a third duality. In general, like a Calabi-Yau three category, we have a duality for this complex. So this is isomorphic to the cotangent complex, but you need a shift because it's a Calabi-Yau 3. So basically, this is a -1 shifted symplectic structure. So we have this. So what is a good thing about having a shifted symplectic structure? So there is a shifted version of Darboux theorem. So Braun, Bussy, Joyce, and Boazis Grosnowski. So in symplectic geometry, Darboux theorem says that the symplectic manifolds are locally cotangent bundles. In the shifted symplectic setting, this is not always true, but still locally, it is a twisted version of a cotangent bundle. So we have a explicit local description. So let me write what it is in this case. So for -1 shifted case, locally, this the moduli of objects in Calabi-Yau 3 category, or in more generally, any -1 shifted symplectic thing as a critical locus of some function on a smooth space. So this is a good thing of having a -1 symplectic structure. It's locally a critical locus of some function on a smooth variety. So it means that even if we consider an arbitrary Calabi-Yau 3 category, locally, it's just similar to the case of Kuiper with potential. So locally, we have this algebra. We have this vector space and a multiplication. We want something global. So we know that the cohomologies are not does not glue globally, meaning that the local version, the cohomology in the open neighbor, the open chart does not determine the cohomology in the global space, but we can glue sheaves here. So we can, if we first glue the purpose sheaf and then take the cohomology, then we can define the vector space. So that's the idea of the cohomological DT theory. So it's done by Braun, Bussy, Dupont, Joyce, Gendroy, and Kim Lee. So if you have -1 shifted symplectic scheme or stack. And additionally, you need something called orientation, which is a square root of the canonical line bundle. If you have this, then you can find a global purpose sheaf on this space, which is locally the purpose sheaf of vanishing cycle. So this is a gluing of the purpose sheaf of vanishing cycle. So we can glue the purpose sheaf. And then the cohomological DT theory studies just the cohomology of this purpose sheaf. So the DT cohomology of some -1 shifted symplectic space is just by definition the cohomology of this purpose sheaf. In particular, we can apply to this moduli of objects in Calabi-Yau 3 category. We get a vector space. So this was solved 10 years ago. And now I will talk about the multiplication part. And this was done recently. So yeah. So the second part is about multiplication. So if you have a Calabi-Yau 3 category, so whole product, basically we want to count extensions. So we will look at the same diagram again. We'll look at the stack of extensions and map to the product. So evaluation in one side and evaluation in the other side. And this map, one arrow is always proper, but this is not smooth or not even quasi-smooth. So we want to relate, we want to map the DT cohomology here to DT cohomology here. So we want to use some structure of this diagram. And so in symplectic geometry, the morphisms that we consider are Lagrangian correspondences. And there is a shifted version of Lagrangian correspondences. And we can see that this actually gives us a -1 shifted version of a Lagrangian correspondence. So we have, so this can be considered as some kind of morphism between these two things. So now I can explain the Joyce conjecture. So I will first write just briefly and then write a precise statement later. So what Joyce conjectured is some functoriality of this DT purpose sheaf. So meaning that the morphisms for shifted symplectic thing, we want to consider it as a Lagrangian correspondence. So given any Lagrangian correspondence, Joyce conjecture that we can relate the purpose sheaf in the both side. I will write the precise statement later. So what we can easily observe is that if we have the Joyce conjecture, then this will imply the conjecture of Kontsevich and Soebelman. Because using this, we can push forward DT cohomology from here to here, then we get the product. So what is solved last year with Kinjo and Sapranov, we proved the Joyce conjecture for this specific diagram. So this form of Lagrangian correspondence. So in particular, we can get the cohomological Hall algebra. So yeah, this is what we've done. Now the thing that I'll talk today is the Joyce conjecture in the more general case, not just in this case. And you may wonder whether why do I care it? Whether this is just the end of the story. Sorry? Sorry? Calabi-Yau 3 categories. It's a conjecture, Kontsevich-Soebelman conjecture. So you get a map from like a DT cohomology for this. So it's about defining some algebra. So if you have a Joyce conjecture, you get a map in this form. This means you have a product multiplication, so you can get an algebra here.
like there is a specific equivalent potential.
Yes.
For each of the local patch. Is there some simple example where you can see that this is a quiver, this is a quiver in one patch, this is a quiver in another patch? I know you're talking about the general construction, but if you have a simple illustrative example, just two patches, two potentials, and
I don't know because exactly this is locally similar to the Keeper situation, but this is like a not actually Keeper because this is arbitrary like a smooth variety, but Keeper case this is like a linear like a vector space. So like algebraically like it's not really locally the Keeper situation. Maybe if you go analytically, maybe you can get it Keeper, but I don't know like whether we can really find some Keeper here.
local koha and the global koha, is there embedding from one to the other?
Local koha and global koha.
Yeah.
Local.
So that M for the global M, and then the patch associated with that with the U, for example.
Yeah. Good question. I was a little bit not precise. So locally, it may not be this part may not be proper. So yeah, if you have some chart like a chart such that this is proper, then it should be like a compatible. The restriction you will have a restriction map. So there's a map from global koha to local koha.
Oh, I see. But that's not guaranteed to some extent.
Yes.
Oh, I see. I see.
Because yeah, this is not always proper if you go to the.
See. So, somewhat counterintuitive. I saw that naively, I saw that I'm growing the local thing, but yeah, but of course I know that you're growing the sheaf itself, but not the koha. I see.
Yeah. So yeah, thank you for the question. So what I want to do is to get this to explain the Joyce conjecture in the general case. And why do I want to do this? So not just for koha, I mentioned that we can define other types of enumerative invariance using the Joyce conjecture in the general case. But also we can better understand this koha if you have the Joyce conjecture in the general case. One thing is that we can relate this 3D koha with 2D koha. So special case, if you have a surface, and for like a moduli of sheath and surface, you have a 2D koha of Kapranov-Vaserov. And from that, if you have a surface, you can look at local Calabi-Yau threefold and get a 3D koha, and we can show that those two are compatible. Those two are the same. So those are the things that we can do with the Joyce conjecture in the general case. So now I want to explain about the result, the Joyce conjecture in the general case. So our theorem is, so we want to look at, because we want to look at functoriality, we want to look at morphisms. So we want to look at Lagrangian correspondence. So if you have an arbitrarily -1 shifted symplectic Lagrangian correspondence, and you also need some compatibility between orientations. So you need a compatibility between orientations. So if you have an oriented Lagrangian correspondence, then we can compare the Perber sheaf in the both side. So we can construct some map, which we call the Lagrangian class. It's a map from Perber sheaf in one side, and then the other side, it lives in different space. So we want to pull back, push forward. So we get a map to the pull back, push forward, and shifted by dimension. So we got certain map, and then this should be an associative. Meaning that if you have a Lagrangian correspondence, this is a kind of morphisms. So you can compose two Lagrangian correspondences by taking fiber product. And then you can also compose this kind of morphisms. Then we can show that those are associated. So this is the result. And I want to mention that the local model was known long time ago, almost 10 years ago. You can see this in Amorim Bambasset's paper, but this is not very difficult. So local model is actually not difficult. Then what's the difficulty in constructing this map? The main difficulty is that this side is perverse, but this side is not perverse. So because this side is not perverse, even though we know how to get this map locally, this local data does not determine the global map. So if you use like infinity categories, then a priori you can glue the local maps, but then you need an infinitely many equal-cycle condition to actually glue the map. So we will use a different approach to get this map, but the main difficulty is that this is not perverse, so we cannot glue the local maps. But why it was easy in our KOA case? In this case, the key idea is that we first locally show that there is an isomorphism between the perverse shift here and the pullback push forward here. So in this case, there is an isomorphism. With some shift. So locally, we have this. So it's not just a map. In this case, we get an isomorphism, but this means that this side is also perverse. Locally perverse, so it's globally perverse. So it's a map, we are asking map between perverse sheaf. So we can actually glue this. So this was an idea to prove this case. Yeah, so that's So that's why there was some fundamental difference between solving the Joyce conjecture in the KOA case and the general case. And so we needed some completely different method. So I want to briefly explain how we construct this map. I just want to explain the idea. So let's start with an arbitrary Lagrangian. So -1 shifted Lagrangian. So this is a case when n is a point, but it's enough to consider this case because you can move n to here and then you get a Lagrangian to the product. So it's enough to consider just a single Lagrangian. So in this case, our idea is that there exists a deformation. So you can get a family of maps, family of Lagrangians. So this will be all -1 shifted Lagrangian. Such that, so this is a deformation. So in this in the general fiber, it's the given Lagrangian, but in the special fiber, it deforms to the following special kind of Lagrangian, which is just a zero section of -1 shifted cotangent bundle. So the idea is to deform the arbitrary situation to this special case. So -1 shifted cotangent bundle is always -1 shifted symplectic. Zero section is always Lagrangian, and we understand this case well. So we want to deform the general case to this special case. So so for this, what we want to get is a map from our goal is to find a map from the pullback of perverse sheaf to the dualizing sheaf shifted by dimension. So this is what we want to construct, the Lagrangian class. So this is our goal. So let's say. So yeah, if you using a joint, you can move this to here. So n is a point, you get a dualizing shift here. So you can move f to here. So this is what we want to construct. And what we know is that for the special fiber, if we deform, for cotangent case, we know this how to construct this map. So there is a map for this case, the cotangent case. This is called the dimensional reduction, shown by Tasuki Kinjo. This is actually isomorphism in this case. So this part is known. So what we want is we want to get some kind of specialization map from this side to this side. Sorry? The dualizing sheaf. If you shrink pull back to a constant sheaf, you get a dualizing sheaf. And the cohomology of this is the Borel-Moore homology. Yeah. So this is what we want to get. We want some kind of specialization map between these sheaves. So we want to use this deformation. And the first thing we did is what we call perverse pullbacks, which we posted maybe 2 weeks ago. So let me just explain this by word. So this is about there exists a family version of the T-perverse sheaf. So we can extend this DT perverse sheaf to families. So we did it because we want to apply it to this situation. Now we have a family of -1 shift symplectic schemes or stacks. So this is the thing that we want to use. So if we write M dot to be the total space of this family, then we get some sheaf here as well. And F dot is also a map in the total space. And it's easy to show that just these two are the same. And what you can easily get is there is a following global map. And we also have a following this. So this maps exist globally by the just having this family version of the T-perverse sheaf. So let me explain the situation again. We want a map from this one to this one. And globally, we have a map like this, so zigzag map. So we have one map in the wrong direction. So our idea is to show that this map is an isomorphism. So this is like the key step. So what I'm saying is that, so if you want to construct a map, and if you know this, how to do this locally, we don't know how to glue it. But if you have a maps globally showing isomorphism, you can check it locally. So we have a global zigzag map, and we show that this map is an isomorphism by looking the local structure of this diagram. Then we can show that this is an isomorphism, so we can compose this diagram to get a map. So yeah, this is how we get the map. So before explaining the examples, I want to explain why why we can consider this as a kind of virtual classes, how we can define invariance from this. So maybe I will use the whiteboard. So how can we define the invariance? So let's recall the usual invariance. So if we have some quasi-smooth derived scheme, or this is just a derived version of having a perfect obstruction theory, then you have a virtual class, the usual virtual class, living in the Borel-Moore homology. So how do you define the invariance from the virtual class? So you first consider the cohomology. So this will of the space. So this will be a space of insertions. So if you insert some cohomology class to the virtual class, so if you cap product this with the virtual class, then you get some Borel-Moore homology classes. And then if L is proper, if L is compact, we can integral, and we get some number. So this is the way to get the invariance in the usual virtual fundamental classes. Now I want to explain how to get the invariance from the Lagrangian classes. So if you have a -1 shifted Lagrangian, what this gives us is a map from DT cohomology to the Borel-Moore homology of L. So using this Lagrangian classes. So if L is compact, we can still push forward this to a point. and we get numbers. So this is how we get the invariance. So the only difference with the usual case in this case is now we insert the DT cohomology class as an insertion. So yeah, so it's just change of the insertions. Then we can still get the invariance. So now I want to give some examples of this to actual moduli spaces.
Just make sure, so they define the invariance, but depend on the different data on the two cases. Like, I mean, one is the DT cohomology insertion, another is the Lagrangian. So do they coincide in some cases?
This one, so
yes.
So
I got the statement, but they're different or like.
There are cases we can recover the first case by the second case.
I see.
So like more generally, you can look at like a quasi-simultaneous morphism, but yeah. So that could be a little bit better. So we can insert further. Okay, let me explain. For simplicity, if you have a quasi-simultaneous morphism, then you can insert from M. Then if L to M is quasi-smooth, you can look at like a conormal bundle, -1 shifted conormal bundle to -1 shifted cotangent bundle. This is always -1 shifted Lagrangian. And if we apply the Lagrangian class in this case, so in this case, you get a map from DT cohomology of this cotangent bundle to the Borel-Muir homology of this conormal bundle. But there is a dimensional reduction. So this is same as the Borel-Muir homology of M. And this is, if this is quasi-smooth, then the classical part is the same. So this is same as the Borel-Muir homology of L. So yeah, when M is also smooth, then this this is exactly the same. But in general case, we can always recover the usual invariance using the second one. So this generalized the usual case.
Second one depended on the orientation of data, right? So
yes.
Was the first one depended on the orientation as well? I can't remember. Yeah.
No, if you go here, there is like a canonical orientation for cotangent bundles.
Oh, I see. So in that case, I see. You choose that one, but I see.
So if you change orientation here, then you differ by sign. So there is no orientation here, but here, a priori, you can make two choices of orientation. So yeah. So now I'll talk about applications. The first one is about the gauge linear sigma model. So what is the input data in the gauge linear sigma model? So we start with some reductive group gamma and representation of this reductive group and consider a potential. And now consider a character, non-trivial character, and consider a weight 1 action here. So this should be equivariant. And I will write G to be the kernel. So this is the data. We also need some stability condition. So there will be a stability condition for the action. So there is an additional stability condition, theta, and some epsilon parameter. Both are stability conditions. So anyway, what is the target in the GLSM? So let's first look at the GIT quotient of this by this group. So you look at the stable locus and look at the quotient stack by G. Then this function descends to here. So you still have a function. And I will look at the critical locus of this function in this space. So this will be X. I will write this to be U. So this is smooth, this is singular, but this will be our target. And here there is a GM action. So we will count curves inside this critical locus. And let me write down the state space. So what is the state space in this case? Because this could be a DM stack, we need to use inertia. So state space will be the dt cohomology of the inertia of x. So this will be the vanishing cycle cohomology in the inertia. So inertia is, so it's just you look at the curves, you look at the maps from finite cyclic curves to U. So this is only for DM stacks. For if you just consider schemes, then you can ignore I and just look at the dt cohomology of X, which is a vanishing cycle cohomology of U. So this will be our state space. So how we get Gromov-Witten invariance in this case? So let's look at first look at the moduli space. So we will look at the moduli space of twisted Cauchy maps to X. So this is a open part inside following stack without the stability condition. So we first consider a map from a curve to the quotient. So x tilde regime. So x tilde is x without the stability. So x tilde is this critical locus without the stability. So we want a quasi map. So we don't just consider the maps to x, but we consider maps to the before taking the stable part. And then additionally, we consider the twisting. So twisting as we consider an isomorphism between pullback of weight 1 line bundle and the log canonical line bundle. So the pair of this data give us a moduli, and this will, after giving this stability condition, we get something DM stack. And yeah, here the C is a Orby-Ford curve, genus G and mark point, Orby-Ford. So this will be the moduli space we care. And if we further assume that this X is proper, then this moduli become proper. So here, now we will look at the evaluation map. So because we are looking at the Orby-Ford curves, the evaluation go to the inertia. So, but for schemes, we can just ignore I. So evaluation goes to X. So a priori, the maps are defined in X tilde, but the quasi-map stability allows that the marking should go inside X. And then you can also consider the forgetful map. This is the Orby-Ford moduli of Orby-Ford curves. And what you get is this map is a -1 shifted Lagrangian relative to this moduli of curve. So what you get in this case is that we get a map from dt cohomology of inertia. So this is this vanishing cycle cohomology. We get a map to the Borel homology of this quasi-map moduli using this Lagrangian class. And we can further push forward to this to the curve. Then we get the cohomology classes over MGM bar. If we push forward along the stabilization map, and this gives us a cohomological field theory. Yeah. So this is way to get a Gromov-Witten invariance. It's just usual cohomology if the potential is 0. Yes. Yeah, I'll just stop here. Yeah.
Okay. Thank you for the very interesting talk. Any questions in the audience? Yes.
Example, so X, I need to be. In this example, I can choose my data such that X is Calabi-Yau of, say, dimension 5 or higher. So should I think of it as an attempt to define DT invariance for any Calabi-Yau or not really?
Not really. So X, well, so sorry, what's the X?
I mean, I can define a GLSM such that X is a Calabi-Yau n-fold for any n, right?
Yeah, you mean just a smooth variety? Yeah,
Yeah.
smooth variety case is like it's kind of Gromov-Witten theory. So if
Right.
X is smooth, like
So
that case, then it's like a usual Gromov-Witten theory.
So okay, you call it DT, but you recover Gromov-Witten. That's the.
This is so this is Gromov-Witten theory.
Okay, yeah, okay.
But the difference is you take insertions from the DT cohomology. So if the target is smooth, then the DT cohomology is a usual cohomology,
Okay.
and you get the same thing as a usual Gromov-Witten invariance. So difference comes when X becomes singular, then you take insertions from DT cohomology, not the usual singular cohomology.
Okay, thanks.
What's the -1 Lagrangian? So the over MGN or
It's over MGN. Yes, I didn't explain this precisely. So this is critical locus. So this is -1 shifted symplectic. But if you take a product with something, you can view this as a -1 symplectic vibration over M. You need to look at this relative over a base. So this is like a symplectic over this base, and this is a Lagrangian over this space. So you can view it as a family of Lagrangians. You choose some curve here, and the fiber is symplectic and fiber is Lagrangian. Yeah, both map to MGN, and things work relative to MGN.
Any other questions? If not, let's thank Dr. Park again.